We begin by adding the desired analog input module to the I/O configuration of our Studio 5000 Logix Designer project. As with any other local module, we provide a unique name, indicate the physical slot location, and, if desired, enter a description of the module. When choosing a communication format, we decide whether or not this controller will own the module. If not, we choose one of the listen-only options. In this example, this controller will own the module, so we will disregard the listen-only options. If we want our data to include decimal values, we choose one of the float options. If we instead want integer data, whether scaled to include fractional values or not, then we choose one of the integer options. For this example, we will use float data. Now we configure the expected firmware revision as well as the desired electronic keying behavior. Since we will configure our channels at this time, we go ahead and check the Open Module Properties box and click the OK button. Moving to the Connection tab, we can adjust the requested packet interval as necessary for the application. In this example, we maintain the default value. In the Configuration tab, we begin configuring the individual channels by selecting our first channel. Initially, we need to specify to which type of signal the channel is wired. In our case, we have a potentiometer wired for 0 to 10 volts that will simulate a pressure transducer, so we choose the 0 to 10 volt option. If we required an offset for our sensor, we could apply that in the sensor offset box. For the notch filter, we choose the local power supply frequency of 60 Hz. In the digital filter box, we can specify a time constant in milliseconds for a lag filter that smooths out the signal. A value of 0 disables the filter. Now we can move on to scaling. Sensors typically have a specified linear relationship between the provided signal and the measured process variable. In our example, we assume that we are monitoring a pressure transducer with a low signal of 0 volts that represents 0 pounds per square inch absolute. The high signal will be 10 volts, representing a pressure of 250 pounds per square inch absolute. Furthermore, we decide to use gauge pressures in this example, so we subtract the local standard atmospheric pressure from the absolute values, arriving at a low engineering value of -14 and a high engineering value of 236. Having configured the scaling, we next need to specify the period between samples taken by the module. For this simple example, we will simply maintain the default real-time sample. Now we can select the next channel and continue our configuration in a similar fashion until all channels in use are configured. Next, we move to the Alarm Configuration tab. We again need to configure each channel in use, so we begin by selecting our first channel. If we plan to use instruction or tag-based alarms, we may simply check the Disable All Alarms checkbox. In this example, we will go ahead and use the module's alarming functionality, so we will leave the Disable box unchecked. Moving to the alarms, we configure our high-high, high, low, and low-low alarms as necessary for the given application. In this example, we are monitoring the discharge pressure of an HVAC compressor, and if the pressure exceeds 200 pounds per square inch gauge, we want to unload one of the cylinder heads. This is our high alarm. Furthermore, if the pressure exceeds 220 pounds per square inch gauge, we want to shut the compressor off altogether, so we set the high alarm to 220 engineering units. We likewise configure our low and low alarms accordingly. Next, we configure the desired deadband. That is, we specify in engineering units how far back into range the process variable must come before an alarm will clear. In our example, we cannot have the compressor and unloader cycling on and off when the pressure hovers around the limits, so we will set the deadband to 25 pounds per square inch. Now, if the high alarm kicks out the compressor at 220 pounds per square inch gauge, It will not be permitted to turn back on again until the pressure drops back below 195 pounds per square inch gauge. We may also configure a rate alarm in engineering units per second. For example, we set our rate alarm to 100 pounds per square inch per second so that, if we experience sudden decompression resulting from a ruptured line, our logic and operator will be able to respond to the anomaly. Clicking the OK button, we may now download to our controller and test operation. Let's configure a quick watch window to take a look at pertinent data for channel 0. So we can add the signal data itself, the rate alarm, as well as the high-high, high, low, and low-low alarms. For this demonstration, we have a potentiometer wired to the channel so that we can take a look at the actual signal that would be coming from our pressure transducer. Here we can see that because the potentiometer is turned all the way counterclockwise, the signal is at a minimum. Furthermore, the low and low-low alarms are currently active. Turning the potentiometer up to about 40%, we see the value climb to around 85 psi gauge. Notice that, although we are above the low alarm of 70, the low alarm still has not turned off due to the deadband of 25 psi gauge. Turning the potentiometer to around 70%, we see our pressure climb to approximately 171 psi gauge. Now that we are within the normal operating range, all the alarms are off. Turning the potentiometer to 100%, we observe our pressure rise beyond 200 psi, turning on the low alarm, and continuing on above 220 psi, thereby activating our high-high alarm. Turning the potentiometer back down to around 60%, our signal falls back under the deadband, and the alarms turn off. Turning the dial rapidly, we see the rate alarm briefly go high. And that's it. Our analog channel is ready for use. As a last step, let's apply a name to our quick watch window so that we can pull it back up when our pressure transducer is wired and ready for testing.